Hi, welcome back. This is still Ken, and we're still in lesson 1 of units, physical quantities, and vectors. And as you recall, in the last video, we discussed on the addition of vectors via the graphical method. In this video, we're going to continue our discussion with the addition of vectors, and we are going to discuss on the analytical method, specifically on vector components. But before we are going to our lesson proper, let us have a brief review first of your right triangle in your trigonometry. Okay, now you have here your right triangle. It's again called a right triangle because one of the angles of the triangle is at 90 degrees, which is at here, at this point here. Okay, now your right triangle has three sides. If you're going to consider this angle here, marked X, okay, or let's say your angle theta. Let's call this one as your angle theta. Okay. With respect to this angle theta here, your right triangle has three sides. You have your opposite side because it is directly opposite to your angle theta, and you also have your adjacent side, which is the side just adjacent to your angle theta. And then the last side, which is the longest side, is your hypotenuse. Okay, so these are your three sides of your right triangle. You have your opposite side, your adjacent side, and then your hypotenuse. If you can recall in your trigonometry, we have these trigonometric identities. Okay, your trigonometric identities. Pardon my handwriting. Okay, you have your very common saw, ka, and then your toa. Okay, so let us discuss this one by one, or review this one by one. So let's go on to first with your saw. So your saw stands for your sine theta, which is equal to your opposite over your hypotenuse. Okay, so the identity saw is for with respect to your angle theta here is equal to your opposite over your hypotenuse. And the second, which is ka, you have your cosine theta. This is equal to your adjacent side over your hypotenuse. And lastly, your toa, this is equal to your tangent theta. You have opposite over hypotenuse. Now, these three trigonometric identities will be very useful in our discussion on your vector analysis. So please take note of these three identities here. The components of a vector is or are what we are going to use in our addition of vectors by the analytical method. So adding vectors graphically actually provides limited accuracy. The reason for this one is because adding vectors graphically depends on the person who is adding the vectors. Like say for example, last time I've shown you how to add vectors graphically using your head to tail method and then your parallelogram method. And I just measured it using the ruler and then your protractor. But what if another person will measure those things? Another person will draw the diagram. It is dependent on who is doing the measurement, because let's say sometimes I don't have clear eyes. So what if I don't read the numbers very well? So I will have a different reading with another person. So in order to resolve that one, it's always best to add your vectors using your analytical method. Your vector components provide a general method for the adding vectors. And any vector can be represented by an x component, ax, and then your y component, ay. Just look at this one here, the figure below. Okay, looking at the figure below, you have here your vector A. Drawn here your vector A. And if you can see, this vector A here can actually form a right triangle, right? And if you're going to project your, if you're going to consider this right triangle here, we can actually have your this side here and then another side here. Okay. Well, this side here below, this is the projection of vector A along the x-axis. So you call it as your AX. And then the side here opposite to your angle theta is the projection of your vector A onto the y-axis. Now this side here is just actually equal to this one here. Okay, so you call this one as your AY. So these are the x components, x component and the y component of your vector A along the xy plane. Okay, so we use trigonometry to find the components of a vector. Like say for example, you're going back again to our vector A here, and then if you have some angle theta here, this side here on the x-axis is just the adjacent side. Okay, if you can remember for your from your trigonometric identities, we have your cos theta is equal to adjacent over your hypotenuse. Okay, now since this side here is your adjacent side, you can find the adjacent side just by multiplying your hypotenuse with cosine theta. Okay, so your AX, which is your adjacent side, is equal to A cosine theta. Remember here that A is your hypotenuse. A is just the magnitude of your vector A. On the other hand, AY, this one here, which is just equal to this line here, okay, is the opposite side. As you can see, this side here is the opposite of, or is at the opposite direction of your angle theta. So since that is the opposite side, you can use your sine theta opposite over hypotenuse identity. So to find the opposite side, you have your opposite is equal to hypotenuse sine theta. So your AY is just your A sine theta. Again, A here is the hypotenuse. Okay. Now your theta is measured from the positive x-axis towards your positive y-axis, as shown in the direction of your angle theta. So again, the x component of a vector is the projection along the x-axis. We have here the projection along the x-axis. If this is again your vector A, you project this one onto the x-axis, you have this projection here. So that is the AX. AX is just your A cosine theta. And the y component of a vector is the projection along the y-axis. So opposite to your angle theta is this side here, which is just actually equal to this line here. That is your AY. Again, your AY is just your AY is just equal to your A sine theta. Okay. This assumes that the angle theta is measured with respect to the positive x-axis. So that is our sign convention of your angle theta. Going going into a counterclockwise direction from the positive x-axis, from plus x-axis. Okay. The components are the legs of the right triangle whose hypotenuse is the length of A. Now, if consider, for example, you want to find for the magnitude of your hypotenuse, if you're given with the legs AX and AY, okay, you can find for the magnitude of the hypotenuse just by your Pythagorean theorem. Recall that your Pythagorean theorem, if this is again your triangle and then this is A, B, and then your C, you can find your C side by your Pythagorean theorem, which is equal to your C squared is equal to A squared plus B squared. And we're going to do the same thing with your components of your vector. You have your AX and then your AY magnitudes. You can find for the magnitude of A here by just your Pythagorean theorem, which is equal to the square root of AX squared plus AY squared. And we can also find for theta, again, if you're given with your AX and AY, from your trigonometric identity tan theta is equal to opposite over hypotenuse. Okay, so your theta is just your tangent inverse of your opposite side over your hypotenuse. Or here you have your theta is equal to tangent inverse of AY over AX. Again, this is your opposite side and then this is your adjacent side. Okay, I hope that is clear. If not, you can please review this video. Now, your vector components can also be positive or negative numbers depending on where it is located on your xy plane. Let us recall that for your xy plane, okay, this is your xy plane. On this side here, you have your positive x. Here you have your negative x. On top you have your positive y, and then below you have your negative y. If you're going to consider here your vector b here, okay, and looking at your vector b, this is at the second quadrant of your xy plane, and projecting your vector b onto the x-axis, you have this bx here. Now your bx points towards your negative x-axis. So thus, for your vector b, its x component is a negative. Projecting your vector b onto the y-axis, which is this one here, it points upward or it's in the positive y-axis. So your by here is a positive component. Okay. Another example is we have your vector c. Okay. You have here your angle for your vector c from still from your positive x-axis, turning counterclockwise. Okay, projecting your vector c onto the x-axis here. Okay, it points towards the negative x-axis. So your cx is a negative. Projecting your vector c on the y-axis here, points downward in the negative y-axis. Thus your cy, so your cy component is a negative or has a negative magnitude. Okay, so your component for your vector is not always positive. So there are instances wherein it's in the second quadrant, third quadrant, or on the fourth quadrant of your xy plane. So your component can either be positive or negative numbers. These are sample exercises on finding components of your vector. You have two problems here, and I will leave this to you as your assignment. Again, the components of your vector can be positive or negative, and the signs of the components will depend on the angle of your vector. These are some of the possible ways in which your vector are projected on your xy plane. If you have here your vector here, for this side here, your ax will be positive and then your ay will be also positive. If on the other hand you have your vector here on the second quadrant, your ax is negative and then your ay is positive. If your vector is on the third quadrant here below, your ax is negative and then your ay is also negative. Lastly, if your vector is on the fourth quadrant here, your ax points in the right, so your ax is positive, and then your ay points down and is negative. Okay, so that is how you're going to find the components of your vectors on your xy plane. Now, let us now finally proceed on to the addition of vectors using their components. But first, let's say you're given with two vectors. Okay, given two vectors A and B. Let us just use this figure here on the right. This is your vector A, and then we have here your vector B. Okay, those are the magnitude and directions of your vector. Let us look at this one individually. But before that, if you can remember from your graphical method, using your head to tail, if you're given two vectors consecutively and then you draw your vector A and then followed by your vector B, you know from your head to tail that the resultant method is just from the origin towards the tail of, or towards the head of B. A straight line from the origin towards the head of your second vector or your last vector B here. So this is your resultant vector. Let us take these vectors individually and analyze each. Let us look at first your vector A. Forget first anything about addition and let us analyze first your vector A. So again, this is your vector A here. Okay. Let us project your vector A onto the x-axis. Projecting that one, this side here is your ax, right? And then projecting it on the y-axis. This side here is your ay. So those are the projections of your vector A onto the xy plane. Let me erase it. Okay, so again, we're understood with that. These are your projections. So again, here, this is your ax, and then here, this is your ay projections. Now, let us look into your vector B. So this is here your vector B. It points here towards there. Okay, let us draw another xy plane and let us take the tail of B to be at the origin. Sorry. Let us take the tail of B to be at the origin. So we have, oh, sorry for that. So we have here our xy plane. And looking at that, let us project your vector A onto the x-axis. This is your new x-axis here. So this is your ex, or this is just this side here. Okay. And let us also project your vector B onto the y-axis. So this side here is your by. Okay. Or moving it towards your original xy plane, this is here your by component. Okay. Now, let me just erase this one. Okay. After looking at your vector A and then your vector B individually, let us look at your vector R. Again, your vector R is your resultant vector, but let's just say that we don't know anything about vector R yet. Okay, so this is your vector R here. Okay, let us project your vector R onto the x-axis. Okay, projecting it, this is your vector R. Okay, this side here is your vector R x. Projecting your vector r on the y-axis, this side here is your vector r, okay, or this is your vector r here, and then this is your vector ry. This is again your rx, and then your ry. Now, have you noticed something? Okay, looking at the figure, you can say, or you can see that your rx, or the r component of your resultant vector r, is just actually equal to your your ax plus your bx. Looking at here, this two sides here, your ax plus your bx is just actually equal to your rx. And looking at your ry here, you can see that if you're going to add the y component and the y component of b, the y component of a, and then the y component of b, you can see that this is just actually equal to the y component of your r. Thus, we can say that that in your analytical method, the x components and then the y components of your vectors are just actually equal to the sum of the components of the individual given vectors. So you have your rx is equal to your ax plus your bx, and then your ry is equal to your ay plus by. If we still have, let's say, two more vectors, say you have your vector c plus and your vector d. Okay, say you have additional vectors, so your rx is just your ax plus bx plus cx plus dx, and then your ry is just ay plus by plus cy plus dy plus plus that here. Okay, so your vector component is just adding the individual components of your individual vectors to get your resultant vector. Now, the magnitude and direction of your resultant vectors are just given by your Pythagorean. So your the magnitude of your resultant r is just the square root of all your rx, the sum of your rx squared plus ry squared, and then your direction is just theta equals tangent inverse of ry over rx. Okay. For more than two vectors, we can use the components of a set of vectors to find the components of their sum. You have your rx is equal to ax plus bx plus cx plus dot up to infinity, depending on how many vectors that you have. And then your ry is equal to ay plus by plus cy plus dot. Okay, you can take all the letters of the alphabet, and you can still use the vector components in the addition of vectors. And the magnitude of your resultant vector is just the square root of rx squared plus ry squared, and then your angle theta is your tangent inverse -1 of ry over rx. That's it. In the next video, we're going to use everything you have learned so far in adding vectors using their components in an example. So get yourself some paper, your pen, and then your calculators. See you!